So yesterday we talked about chemical equations. We introduced you to, or reviewed with you probably, word equations, where we just have the chemical names, and then the arrow meaning to produce or yield, and then the names of the products. And then we finally introduced you to the chemical equation, which then puts the chemical formulas in that equation. Sometimes that chemical equation is called the skeleton equation, all right? Your textbook might make reference to what is called the skeleton equation. And the skeleton equation is just a chemical equation that hasn't been balanced yet, and that's what we want to talk about today. We want to talk about what it is to balance a chemical equation and why we have to do such a thing. The answer to why we have to do such a thing has to do with masses in chemical reactions. How does the mass of a reactant compare to the mass of the products in a chemical reaction? That you might think is a simple question. You might even have a hypothesis on that, and I'm going to get you to write a simple little hypothesis in a moment, because in a moment I'm going to demonstrate an experiment on that, a conservation of mass experiment, and we're going to do a little analysis. We're going to predict, how will the mass of the reactants and the products, compare to each other? In other words, will the mass change? And so we are going to fill this all out in a moment. So you could build this grid right now as I do some talking. I'm going to tell you what the reaction is in a moment, so you can leave that blank. I'm going to tell you what the chemicals are. We'll add that in. You're going to do a quick little hypothesis where we're going to get the reactants ready, weigh their mass, and then do the chemical reaction, and then weigh the mass again. We want to see if the mass changes. Ignore that, my dishwasher. I thought it would be done by now. It's just finishing. Sometimes you got to do dishes. It's just the way it is. And then we're going to take a look to see what the observations are, and then we're going to talk about why that is the case. The dishwasher is discharging the rinse water at this point as we speak. The reason it's making all that exciting noise is because it's a portable dishwasher, which means it's got two hoses going there. One is an input hose that goes into the dishwasher, takes the water in from the tap, and then as it's done with that water, the second hose discharges it out of that outlet into the sink. Yeah, it is kind of neat. Because we can move it from room to room and do dishes in various spaces. But it takes a special tap, and we only have one, and it's right here, so really I can't move it from room to room. I'm the only one who gets to use the dishwasher, and it's awesome. So will the mass change between our reactants and products? Before we actually get to that, this question was posed by a chemist, and I've shown you this book already. Have I shown you this book? Mr. Lavoisier, a very important guy. He was really the first chemist that decided maybe that we should start measuring things very carefully and very quantitatively. Did I tell you about Newton? Did we talk about Newton, and did we talk about Aristotle and all that stuff? I can't remember what stories I tell anymore. A little bit, very little bit. Because physics at the time of Lavoisier, right? Physics was kind of brought into the modern ages by Sir Isaac Newton, and that was done in the late 1600s, early 1700s. Essentially, what Newton did was he made physics a mathematical science. In other words, if you wanted to, predict where a billiard ball would end up on a pool table after striking it, you could use Newton's laws of physics and forces to predict what would happen, and you'd be correct if you did all your calculations correct. So physics was really the cool science back in the late 1600s, early 1700s, thanks to Sir Isaac Newton, because it had predictability, because we could use the physics that Newton proposed to predict what would happen to a very simple system like a billiard ball rolling across a pool table. Chemistry at the time was not predictable because chemistry evolved during the Middle Ages from something called alchemy. Have you heard of alchemy before? Yes, no? It was kind of the pseudo-science that some alchemist would do if he worked for the king or something and would be able to maybe, take a substance and mix it with another substance so that it would explode, like maybe make some gunpowder, or perhaps take a substance that was unknown and do some simple tests to maybe predict what was, not predict, but to test what was in it, kind of like testing for ions. Having no idea why they were doing it, just really a bunch of recipes. But it wasn't predictable. There were many alchemists, I'm sure, that lost their lives as they attempted to mix up some gunpowder for the king that didn't have, say, the recipe exactly right, because it involved a lot of dashes of this and mixtures of this. So, maybe making an unstable compound that, ended up killing them. Now, it was Lavoisier. He was a Frenchman, and again, this is in the early 1700s, who realized that chemistry was really kind of all in shambles because nobody was measuring anything. No one was taking really good numerical data. So he decided that he would go through all kinds of reactions that alchemists would talk about and would systematically measure everything very carefully, all right? He actually invented all kinds of analytical equipment, and this book here is a reproduction of his original book, but it's an English translation, and it was translated probably about 100 years after Lavoisier wrote it, so we're talking early 1800s. But this is a reproduction of that book. It's not like it's a real copy. It's like just a reproduction. I had to read it for a course in university. Anyway, Lavoisier invented all kinds of different types of chemical equipment that we still use today in various forms to undertake all kinds of different chemical reactions, all right? The neat thing, though, was that he was measuring them. Now, it's not that, okay, Lavoisier was pretty smart, but there was another thing that was happening at the same time that allowed him to measure those things. Ignore the wastewater. At the time, just before, in the 1600s, they didn't have fine enough mechanical equipment to create a scale that was fine enough to measure tiny masses. They could make a simple balance, right? And if the masses were big, like if you were measuring sacks of wheat or something like that, they could easily measure those masses. But if you were dealing with tiny little amounts of chemicals, they couldn't be measured accurately enough. So that also prevented chemistry from becoming a cool science, right? So also at the time in the early 1700s, I'm trying to think, the word isn't engineers, but people who build little tiny machines, don't even know what you'd call that, engineers, were able to build scales that were fine enough to measure tiny masses. There's another reason for that. What they were trying to do is they were trying to invent a watch that could be taken on a ship, right? Because at that time, everybody was taken off from England trying to explore for various types of things, right? And they had to figure out where they were on the Earth, and they needed to know what their latitude was. And the only way they could know their latitude was to know what stars were above them, but then also to know how long they've been, traveling, because as you know, the stars move above us in the sky, it's the Earth moving below us. But they needed to know what time it was. They needed to know exactly how many hours they'd been at sea. And you can't use a pendulum clock at sea. If you use a pendulum clock at sea and the boat's going back and forth like this, the pendulum gets all messed up. And so it doesn't keep proper time. So actually some king of England put out this great big monetary prize. I don't know what it was, but for someone to build a timekeeping device that would be able to function at sea, and essentially to build a watch. Now, all the interior workings of a watch are the same types of parts and pieces that are needed to build a really good scale, because you need to have things move very tiny little amounts in order to measure small masses. So two things were happening. Lavoisier was saying, hey, we need to measure things, and because they were trying to invent a watch, history was allowing engineers to build scales that could measure things finely, very, 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 fine amounts. And it was this that allowed Lavoisier to do an experiment quite similar to what we're going to do, that allowed him to test how does the mass of reactants compare to the mass of products, all right? And it's a very, very important little thing. So let's go ahead and do this. So to tell you right now, I'll tell you the two chemicals that we're going to use. I'm going to get my goggles out here. Get ready. The two things I'm going to use is calcium chloride aqueous and sodium carbonate aqueous. So we can put those, let's put the formulas here, all right? So calcium chloride aqueous is what we're going to have. What's our formula for calcium chloride? Again, you should always have maybe a periodic table nearby. And you know what? That's a good thing to do. When you start doing chemistry, the periodic table's your buddy. If I'm going to ask you calcium chloride, you need to be thinking, how many electrons? What's the charge going to be? I got to cross over charges. So always have your periodic table nearby, because we need you to, as soon as I say calcium chloride, boom, I need you to be able to write down calcium chloride. So what do we have for a formula for calcium chloride? We've taken some time to think. What do you got, Megan? Yeah, very nice. CaCl2, and it's dissolved in water, so what letters do I put behind this? Yep, AQ, aqueous, excellent, AQ. And we are going to react that with sodium carbonate. So once we've had some time to think and digest that information, if someone could supply me with a formula for sodium carbonate, that would be appreciated. Marissa, what do you got? Na2CO3, right? And again, I apologize for the dishwasher. I thought it'd be done by now. Anyway, good. And it's also dissolved in water, so AQ. AQ. Excellent. AQ. Now, I'm going to tell you right now that, and Shane noticed this yesterday, this type of reaction is one where they trade partners, right? Where they're going to trade, and you observe that. Which means the sodium is going to go with the chloride, and the calcium is going to go with the carbonate, all right? So I need a formula for sodium chloride. I need a formula for sodium chloride. We'll pause for thinking and finding of charges and crossing over. Lots of little things to always think about in chemistry. That's where this is going to start to build and grow big. So we can either take it head on or we can panic. Don't panic. Sodium, what's the charge? Chloride, what's the charge? Cross it over. What do you got? NaCl? NaCl, and I'm not going to put any state behind that quite yet. And calcium is going to go with the carbonate, so I need a formula for calcium carbonate. Got to find the calcium, got to find the charge, got to find the carbonate on the table with carbonate, got to cross it over. What do we got? Olivia, what do you got? CaCO, there should be a 3 with that. CO3, right? Carbonated CO3. And I apologize for the squishiness. CaCO3. Excellent. Okay, let's take a look at this chemical reaction. By the way, it's 2 and 2, and they both cancel out. So here's what I'm going to do. I am going to take some of the sodium carbonate. What's that? Do we have to put which first? Oh, predict. Yes, but I'm not going to mix it yet. But you can predict right now if you'd like. I'm just going to get my reactants ready, and then I'm not going to do the reaction yet. But yes, you can predict now if you'd like. But let me first get the reactants together. I'm going to take some of the sodium carbonate, and I'm going to put it in this Erlenmeyer flask. All right? Right there. And eventually I will weigh it. And I'm going to take some of the calcium chloride, and I'm going to put it in this little beaker, or sorry, this little test tube. And hopefully I can do this without making a complete mess. Oh, this is very imperative that I don't screw it up. I was going to pour it, but if I spill it, it'll make a mess. I need to get a little transfer pipette. We've seen these transfer pipettes before, right? That's not a big deal. I just wanted to make sure that I don't make a big mess. So I'll draw some up in here. Transfer it into here. All right. Okay. Put that in here. Oh, no, I don't want that stopper on it. because I don't want it to. So now here's the thing. I'm going to put this in here very carefully, like so that they're not mixed together. They're not reacting yet. Everybody see how I did that? Okay. And now I need to put a stopper on it because I want this system to be closed. We call this a closed system. In chemistry, there are three types of systems. We have something called an open system. And an open system isn't very exciting. It means it's open out to the air. We've done some reactions with some open systems. When we tested for ions, right, we just had that little well and we put some drops in it. We could see a change in color, right, or we could see a precipitate form. We call that an open system because some of the liquid could have spilt out. And it wouldn't have been all we can see in an open system is things like color changes. This is a closed system. This closed system allows us to look in and out, so we can see it quite nicely. We can see the energy if it comes out, but it keeps all the matter inside, so we don't want any matter to escape. That's because what we want to check is to see if the mass changes. So if I didn't close the system and I dumped some out, of course the mass would change because I would lose some, right? So I'm using here what is called a closed system. The third type of system that we can encounter in science is what's called an isolated system. And in an isolated system, we don't even want the energy to escape. An example of an isolated system would be a thermos, all right? So let's say we did a chemical reaction in a thermos, then we would have that heat, if it was produced by the reaction, stay inside. Because sometimes we want to measure heat energy, right? Sometimes we want to measure exactly how hot a system got or how cold a system got without, just touching it. We want to actually measure it. In this experiment, we're not worried about any heat generated, so we don't need an isolated system. We just want to worry about what happens to the matter or the mass. So we need a closed system, and that's why I put that stopper on it. Okay, so at this point, we'll turn on the scale. And I was going to switch over to here so that we could take a look at what we're looking at. And I can't switch over to here because I don't have any power here. There we go. And I didn't plug in my cord, which means that's also a failure here. Failure to connect. There we go. Connecting the cord, which means I got to move everything over a little bit because I forgot the cord's not long enough. And I just wanted to give you a chance to take a look at that, and hopefully it's not upside down. So let's switch the input and see what we get. Input. And it's upside down, of course. Zero looks like zero upside down. Oh, well, that's okay. We'll figure it out. We'll churn our brains around and we'll write down what the number is. So I'm going to put this on the scale, like so. Can you read upside down? What's that say? 154.3 grams. Excellent. And now for the experiment. I'm going to mix the chemicals together. We're going to have a chemical reaction take place, and then I'm going to weigh it again. And your prediction is, will the mass change? So you can write down yes or no. Will the mass change? No, that's not for your prediction. In the explain, we're going to talk about what we see in a moment. All right? In the explain, we're going to talk about what we see in the end. All right? So did you make a prediction? Will it change? You're going for a yes. Awesome. Good job. Okay. Now, there is a reason why I'm doing this as a demonstration. Other teachers sometimes do this as a full lab, but I don't. I like to do it as a demonstration. Okay, so let's take that off. 154.3. I'm now going to carefully pour it over so that the liquids come together. All right. All right. We can see there. Have we had a chemical change? Yeah, we've got a new color. It's actually a precipitate has been formed. Let's now weigh it again. And what do we got? 154.3. All right. So, did the mass actually change? No. No, it did not. Let's switch this back. Input. So, will there be a mass change? You put that right there. Oh, explain. Oh, there was an extra explain in there. I'm not worried about that. You're right. That was supposed to be explain it, but I'm not worried about it. Observe, did the mass change? You can say, no, the mass didn't change. We can put here before, no E on that. We've got 154.3 grams, and after, we've got 154.3 grams. Therefore, no mass change. All right? Okay, again, don't worry about that middle explain. There's a reason I do this as a demonstration as opposed to doing it as a big, long lab report. I remember doing this in high school, and I remember being absolutely, and did I tell you this story before? This is the experiment I was talking about, being absolutely disappointed with it, because in the end, it doesn't change, all right? And that's because when we have a chemical reaction, and you can put this down as your explanation, in a chemical reaction, atoms and ions change places but the total is the same in the end. Yep.
In a chemical reaction, why do say the calcium and sodium,
why do they switch? In this case, and this was what I mentioned yesterday. This is a particular type of chemical reaction called a double displacement reaction. All right, and I've got to let's save this for when I get to talking about types of chemical reactions to the end of the week, because it's going to take a fairly long discussion, and I want to save it for when we get closer to that spot. Is that okay? Does that make sense? It has to do with the ions being able to move freely, just like we talked about the conductivity. And when certain ions bump up against other ions, sometimes they make a solid, all right? And so what we're seeing is they're bumping up against all kinds of different ions, but when a calcium ion bumps up against a carbonate ion, it sticks together tight and makes a solid, and the solid comes out. So it's not like they're necessarily trading positions consciously. They're randomly bumping up against each other, the ions are, and when they bump up against a certain pair, some of them make solids and precipitate out, okay? I ended up explaining it, but I'll do it again when we get to that point, all right? Anyway, it doesn't make any difference what that explanation was about. In this case, we have the same mass, and that's very important. So what does that mean? That means then that we must balance chemical reactions in order to fulfill the law of conservation of mass. Now, the reason I tell you the story about Lavoisier is because Lavoisier discovered this law. And the reason it's so important is this law is what makes chemistry predictable. We now have the ability to take reactants, measure masses, and predict exactly how much and what type of products we get. So it's now a predictable science. We can use it to predict what will take place. So a chemical equation must reflect the law of conservation of mass. That means the mass of the reactants must equal the mass of the products. This is done by balancing the chemical reactants atoms and the products atoms. Each atom has a mass. We haven't looked at the mass number on our periodic table because we haven't needed it, and we're not going to need it in this course. In grade 11, we will use the mass numbers. But every one of these big numbers here underneath the elements represents the mass of that particular element. And each atom of each element type has the same mass. So if we balance the atoms, we're balancing the mass because they all weigh the same amount. Oh, good to go. We've got some people still writing, maybe doodling, finishing here. So let's go about by balancing some reactions here. This is going to be my first example of some balancing. There are many different ways in which I've taught this. And I have taught this to a vast degree of academic ability. And I'm going to start out with a very remedial way of teaching how to balance. And I'm hoping that we can get to the point where we don't have to take as many steps and just get straight to the balancing. And we will. I've said it before, you guys are a smart bunch. I'm very confident I could probably skip what I'm going to do here at the beginning. But just to make sure I cover everybody, I want everyone to take a look at the way where this comes from, okay? All right. So normally, when you balance a chemical reaction, you put big numbers in front of the chemicals in order to get the atoms to be the same on both sides. Those big numbers that we put in front, we call a coefficient. A coefficient is just a fancy way to say a number, all right? So if I take a look at this reaction right here, how many sodiums do I have on the left-hand side? How many sodium atoms are there? And this is really easy stuff. We're really taking baby steps. How many sodium atoms on the left? One. Good. Nice job. See, there's one. It's right there. And how many sodium atoms are there on the right? How many sodium atoms? Yep, Megan? 2. That's not balanced. This chemical reaction is not balanced. I have 2 sodium atoms on the left, and I've only got 1 sodium atom on the right. Right? Sorry, I did that backwards. You looking at it. Left 1, right 2. Right? Let's look at the oxygen. How many oxygen atoms? We're balancing atoms. 2. And how many oxygen atoms here? 1, because of this little subscript is a 1, right? Everybody remember that? Is that good? So this is definitely not balanced. So what do we need to do? We need to put some big numbers in front of here in order to make them the same left and right. And I can put a coefficient in front of any one of those reactants or products in order to make it the same. It's like a multiplication factor, okay? When I'm balancing, I can only add coefficients. I cannot change these little subscripts because the little subscripts come from the crossover. The little subscripts, that number, is defined by what the chemical is. So sodium is just a metal. It's not a Hofbrinkel gas. The only way I can write it down is Na. I can't write it down as Na2 because that doesn't exist. And oxygen is a Hofbrinkel gas, so I write it as O2. I can't write it as just O. It might be convenient in order to make it balanced, but it would be wrong. So I can't change the little numbers. I can only change the big numbers that we're going to put in front of it. Does that make sense? Okay? No, you don't like it? You'd like to change the little numbers, Megan? No, I've embarrassed Megan. Okay, I'll pretend I didn't ask. So we can't change the big numbers. All right, so this is what I've done in the past. I've taken an accounting of all of the numbers. Now, what I'm doing here is overkill. It's way overkill. There's a quick way to do this, and we're going to get to the quick way. But what I like to do is I like to write down here, underneath here, I'm going to make an accounting of the Na atoms. All right? I'd like you to write this down the first time. In the end, we're hopefully not going to have to do this, just like the crossover, right? hopefully we can do the crossover in our minds. We don't have to write this all out. And I'm going to write down the fact that right now I have, and I'm going to use a different color. If you've got two different colors, that would be great. Pen, pencil, that'd be awesome. Again, some of you might already see that we could balance this up in an easy way, and that's great. But if you've got two different colors, that's great. So I'm going to write a different color here. I have one Na atom times 1 equals 1. Let me show you where my numbers came from. This number 1 came from right there because there's no subscript, so there's one Na atom, okay? This number 1 came from right there. Because there's no coefficients, it means 1, right? When chemists deal with 1, they don't write it down. Everybody okay with that idea? So I have one Na, and each Na has one atom, so there's only one Na on that left side. Okay? I'm now going to do the same for the rest of the atoms. So for O, I have, this time I'm going to make it pink, 1, O2. And how many atoms are in each of these things? 2. So I have 2 O atoms. Because there's a 1 in the front, there's a little 2. Make sense? Okay. Now, for this last guy, I'm going to have an Na run and an O run. You see what I mean? So I'm going to have, again, I've got the number 1 right there and the number 1. And in this case, how many NAs are in each of these? 2 equals 2. And how many O's are in this thing? 1 times 1 equals 1. I'm hoping we can all handle that in our brains, right? You could probably go, oh, well, yeah, that makes sense. But that's what you're thinking. We're going to write it down a few times, but we won't do it all like this. It'll take us forever to do it like this. But it's getting you to start thinking. Okay, now, when you balance, you can only change the big numbers, the coefficients. I'm going to put a little note down here. Only change the coefficients. I got to say it like that. You know the way it works. And the coefficients are the big numbers. All right? They're the big numbers we put in front of it for a balanced chemical equation. So let's start changing some of our numbers. How many NAs have I got? 2. So I could maybe change that to 2, right? But then I've also got a 2 here, and I got to change this to a 2, right? You see that? I don't know if you noticed, but if I change this, I'm going to change this, which is going to change this. So I want to start with the O's first. Okay? Let me show you what's happening. I'm looking at the O's. What do I want to turn this into? Okay, so I can do that. I can turn that into a 2. But in order to make this mathematically correct, I got to change one of these numbers, and I can only change the big number. That's it. And that's this one right there, isn't it? Right? Because I can't change this 1. It's locked into position. So I can make that become a 2 by putting a 2 here, right? But then what does that automatically do to my O? What does it automatically do to my Na? Because now this is a 2. And what's this now? This is a 4. I didn't change color. You'll be able to adjust. See what happened there? Okay? Now what is my next move? Yep, Megan? I can force that to be a 4. And if I do that, what do I have to do mathematically to make it true? Yep. I change the coefficient to a 4. If I had started with the NA, I would have fixed it, but then when I went back and changed the O, I would have been in trouble. I would have had to change again. Sometimes you got to bounce back and forth. The most important things that you have to know when balancing. You cannot change the little numbers because they're determined by the formula that we get from the crossover, but you can change the big numbers. And you change them so that each of the atoms of each type are the same on either side. Now, like I said, this big accounting method that I did, we're going to get rid of it in a minute because we want to go quicker than this. But that's the thought process. Yes? Yeah? Sorry, say that again. I changed this one. And you want to squeeze an O in between, a 2 in between here? You can't do that because sodium oxide is a compound that has 2 sodium atoms welded onto an oxygen atom. So you can't just change the essence of sodium oxide by sticking a big number 2 in the middle of a formula because they're stuck together by their chemical nature from the crossover. So you cannot do that. You have to do the top one, which means if you're going to change one of the elements in a compound, it will automatically change the other element by the same factor. That's a great question because that's a common mistake that students do. They want to squeeze it into the middle and be done. But you can't because sodium oxide is Na2O, you can't just change the amount of oxygen in sodium oxide. That's built into the nature of sodium oxide. That's a good question. Shane?
So this now is balanced.
Is it? Do we have it all balanced? Let's do a quick check. 4 times 1 is 4. 2 times 2 is 4, right? 1 times 2 is 2. And 2 times 1 is 2. That's a balanced chemical equation. Okay? Does that take care of it? There's no 1 written after the Na2O, but it's implied that there's just 1. Yes?
When you're making a balance, you start with exotic.
Not necessarily. I'm going to show you now, and we're going to do some more complicated ones. And there's a series of little tricks that you can use depending on the type of chemical reaction it is. So I'm going to tell you a few tricks here in a moment. This was to show you 2 things. 1, we can only change the big numbers. 2, we can't change the little numbers. Okay? And I guess 3, you can't squeeze a big number in the middle of a formula. That's a great question. Don't be embarrassed by the question. It's an awesome question because students try to do that. Why? Because it's a shortcut. And it's a cheater shortcut. It's incorrect. You can't squeeze it in there. Okay? Now, all of this writing, and I'm hoping as we try to check for balance, is not needed. We can do it up here. Right? We can do it as quickly as this. 4 times 1 is 4. Without having to write it out, right? 1 times 2 is 2. 2 times 2 is 4. 2 times 1 is 2. Balanced. Okay? I just wrote it out in big so that you could see it on that first try. Let's take a look at some other examples. Okay, so 3 main types of balancing chemical equations. So here I'm going to give you some hints on how to do these things. Really, there are, what we're doing, the way we balance is something called inspection. In other words, we're looking around and we're fiddling with numbers until we get it. There's really no magic to it. You bounce back and forth, you change a number, does it change something else? You have to go back and change, etc., etc. So you just kind of bounce around and balance, all right? And here we're saying that there's three main types. There's all kinds of more different types of balancing. You know, when you continue on in chemistry, we often have ionic equations that need balancing. We're going to do something eventually called redox reactions that need balancing. There's all kinds of different ways and complicated balancing methods. We're introducing you to some simple methods here. So there's obviously more than three. So no polyatomic ions. In other words, none of those ions that are on our sheet. You know the polyatomic ions in the middle of the sheet? The carbonate, the nitrate. This doesn't have any of those. And the easiest way to do that is if there are, check for lone atoms. Check for atoms that are by themselves. And always balance an atom that's by itself last. If there isn't anything by itself last, then you might have a Hofbrinkel one to balance last. All right? You always go for the simplest thing last. Why do you think that is? Well, let's take a look at that first example. In this case, you've got really two options, don't you? There's two simplest things. What could you balance last here? Yep. Hydrogen or oxygen. Why do you think we would put as our last number one of these as opposed to putting our number last as one of these? What happens when I change this number here in front of the water molecule? Yep. I've got to change all the other ones, because if I change the molecule last, I'm going to have a change in the H's and a change in the O's. If I put a number in front of the H or the O, I'm only changing one thing. And then that doesn't mess everything else up. Okay? What do you want to start with? We start with H's. How many H's on the left? 2. 1, 2. How many H's on the right? 2. Awesome. This is easy. That's great. How many O's on the left? 1 times 2. How many O's on the right? 1. Now, I'm not going to write out all those nice little times table that I just did. How am I going to make the number of O's on the right become 2? Yep. Put a big 2 in the front. Now, I've changed the H's, but that's okay. That doesn't bother me. But I've balanced the O's. Now we go back and recheck. What do I need to do in order to fix this? What do I need to do, Connor? Put a 2 in front of the first H. There are 4 H's there. There are only 2 there. I put a 2 in front of that and I've balanced it. Notice I didn't write out all that big timetable stuff because it's happening very quickly up there. We can quickly put it together. But that first time I wanted to show you where it all came from. All right? Wilson, make sense? Okay? So a quick check. 4, 4, 2, 2. We've balanced it. Good. We're moving too fast. Are we feeling a little better there after that little chaotic bit in the middle? All right, let's do a few more. So example 2. You'll notice we don't even care about the physical state it's in. When you're balancing, we're not worried about that whatsoever. We don't care about that. We're just worried about making the numbers add up. We need them to be the same on both sides. Are you already got a plan there, Shane? Oh, you got a question? All right, we'll take the question. What do you got? Yep. In some chemical reactions, depending on what we're doing, we do care about the state. All right? So in that reaction that I just did earlier on, we had a new solid formed. It's all settled out on the bottom right there. So if I'm studying this particular chemical reaction, not necessarily for mass, but for the existence of a solid, I do care about that, right? In this case, the lesson is on balancing, right? So I'm not worried about what physical state it's in right now. I'm just worried about getting the numbers the same. So it's simply just because that's what we're focusing on right now. Which one do you think we should do last? Yeah, what do you think, Megan? You want to put a number in front of the NCl3 last? Yeah? As soon as I change that number there, it's going to change both N's and CL's. So whatever I've done work on that, it will change those. No, I do not want to do the NCl3 last. Yeah, what do you think? Either the N2 or the Cl2. That's excellent, that's good. Now it's going to turn out that only one of those is going to be working for us last. And there is a way to kind of figure it out, but I say we just go by inspection. Let's just kind of dive in, all right? So what do you want to do? Let's have a plan. We just need to start. By inspection, you dive in. What do you got, Megan? Because you want to take care of this too, correct? All right? Yep, that's good. So I'm going to put a 2 here, 2. So now our ends are taken care of. How do we finish it? How are we going to do this? Who's got it? Who wants it? You got something? You're looking at the CL thing? How many CLs have I got on this side? But there's 2 of those things. So how many in total? 6. So how many do I need over here? I need 6 atoms as well over here. That's correct. So 3, correct. Boom. That's the logic. All right? 3. Okay? So as soon as you do the 1 and you're happy with it being balanced, you can ignore that atom, the N. Just ignore it. So then 3 times 2 is 6. I need 6, so I need a 3, 6. All right? All right? So once you've balanced the 1 and you're happy with it, ignore it. Then you apply that coefficient onto the next one. All right? Let's do it some more. It's fun. All right. This time I've given you a little word equation. So we need to use our ability to do formula. And that's the way chemistry works. We teach you something, and then we build on top of it. You must master it. It's not like in, I don't know, English. If you don't quite read that novel, it'll go away. There'll be a new novel next. It doesn't work that way in chemistry. Because everything we do builds on the previous thing. Formula for aluminum, just aluminum, aluminum metal, and it's not a Hofbrinkel. So what is its formula? Yep, where's it? Al. Very simple. Al. It is a solid, but we are not worried about that. Formula for oxygen. O2. It is a Hofbrinkel. O2. Formula for aluminum oxide. We've got to use our crossover. We can't just make aluminum oxide by squeezing the reactants together. You need to check the charge on the oxygen, the charge on the aluminum, cross it over, just like we did. So we've got to be able to do that. What do you got? Yep. Al2O3. Notice we didn't just squeeze it together to make like AlO2. That's incorrect. That's not the way aluminum gets together with oxygen. It gets together like this. Okay, now we dive in. There is one that is even more simple this time. Which one should we do last, do you think? Which one should we do last, do you think? What do you think? Aluminum, because it doesn't even have a 2 with it. That's even easier. Which means we've got to start on the oxygens. And we're running into this thing that you're going to find in chemistry all the time. 2 and 3. This 2-3 situation. You're always going to build a common factor. What number are we working with here if we're dealing with 2 and 3, Shane? 6. So how do I make these things work together to get a common number? Yep. No, I don't need to put a 6 there because 6 would get me way too many. Yep. Yeah, if I put a 2 here, how many O's am I dealing with now? 6. And then how do I fix this? Yeah, Wilson, what do you got? Yep, still looking at you, Wilson. 3, because there's that common factor of 6. Put the 2 on the one and the 3 on the other. Gives you the common factor of 6. And that happens quite a bit. And now, what do I need to finish this? Shane? 4 in front of the aluminum. All right? Looking at the time. Yeah, we'll keep going. I don't know if we'll get to the homework. I'll assign some, but oh, this is another one. This is a good one. Yeah, let's keep going. Got to do them all. You guys need practice. So again, if you use the logic, you should be able to guide yourself to what you should start with. What should I do absolutely last here? Which element should we balance absolutely last? We're getting the same people, but I want to get some others. Yep, what do you think? Yeah, I agree. So what do you think we should do second last? H2, because it's next complicated. Well, by that logic, what element should we do first? Yep. Notice it's by itself, and it has a coefficient of 1. So if I put a number in front of it, it's really easy math. You see what I mean? This is by itself, but it has a coefficient of 2. It's slightly more complicated. And now by the logic, what should we then do first? Sammy, what should we do first? But which element are you focusing on? Which element do you want to balance first? Oxygen. That's maybe the answer I'm looking for better. Maybe that was the better way to ask the question. So don't think about which chemical to work first, but which element to balance first. You see what I'm saying? So you're right, oxygen. What have I got here? How am I going to balance this oxygen? Somebody got a suggestion? Sammy, why don't you keep rolling here? I think you got it. How many O's have I got on this side? Sorry, I can hardly hear you. You got to be loud. 1. How many on this side? So what do I need over here? A big 4, because that's all I can do. Okay? And we've decided that we're going to do H next, right? Who wants to take on the H's? Justin, go ahead. 4 in front of this, because you've got 8 and you need a 4. Excellent. You have it finished off. And is that good? We got it balanced? I like it. All right? So maybe I should rephrase it when I say what should we do first, not thinking of a chemical, but think of the element you want to balance first. Right? So I look at that and I see F's and O's and H's. I want to do the O's first. All right. What if they have polyatomic ions in them? To be honest, I find teaching balancing one of the hardest things for me to teach as a teacher, because there are many little things and tricks that you learn by practice, and to write them all out and tell someone all the little tricks is sometimes difficult. I forget to tell you, oh yeah, maybe we should think of it in terms of oxygen. You know what I mean? So it's difficult. Practice is the best way to get good at these. There are many chemical reactions where the polyatomic ion stays together, the nitrate or the sulfate or the carbonate. And in this reaction here, as you're writing, you'll notice there's a nitrate over here, and there's a nitrate over here, which means the nitrate didn't change. It means the nitrate did not break down into its elements like nitrogen and oxygen. If a polyatomic ion does not break down, in other words, there are no N2s or O2s, then treat it as if it's its own element. In other words, balance the nitrates, as if it was like balancing an oxygen. Again, we could do the copper last, and we could do the silver last. So what's left? Well, you might be thinking nitrogen and oxygen, but notice they're stuck together as a nitrate. So why don't we just balance then the nitrates? Okay? How many nitrates are there on the left? How many nitrates? And this is where it gets a little tricky, yeah? No, there's 3 oxygens, 1 nitrate. There's 1 right there. It's an entire nitrate, which is made up of NO3. Okay? How many nitrates are on the right? There are 2 nitrates. So we can balance the nitrates by putting a 2 there. We've balanced the nitrates. You could do it with individual nitrogens and oxygens, but why bother adding those extra steps when they're staying together? Now we just have to balance our metals. It's looking like copper. How many coppers? And how many coppers? 1. And what do I need here? I need a 2. All right? So if it has polyatomic ions and they're not falling apart, just balance them as if they're their own thing. You'll know if they fall apart. If I had some nitrogens and some oxygens and that nitrate wasn't there and I had an N2 and an O2, right? Then you'd have to balance that as if it were N's and O's. Okay? We got one that we can do. The last one we're going to do is combustion reactions. They're fun. Oh, and look at there. I hardly left enough room to write the coefficients. That was stupid. I needed more space over there. Combustion reactions we're going to learn are a fuel reacted with oxygen. In this case, the fuel contains carbons and hydrogens, so it will always produce carbon dioxide and water. We will talk more about that when we get to the types of chemical reactions. But that's a standard type combustion reaction. And I don't think it would have been too big of a stretch that you would have did the O last. That's excellent. That's a good way to do it. But I find it's the easiest to do C's than H's than O's. And it's fairly straightforward. Carbon dioxide has 1 C in it. So for every C that's in our fuel, that will produce a carbon dioxide molecule. So how many C's are in the fuel? 2. So how many CO2s will we have? 2. Now the H's. Notice there are 2 H's in each water molecule. That means for every H, I will have half as many waters because I need 2 of those H's to make each water. So if I have 4 H's, how many waters will be produced? 2, right? 2. When you have combustion and you're balancing your O's, you're going back to this side, you need to add up the O's from here and the O's from here. So how many O's are in my 2 CO2s? 4? Well, you could write it down if you'd like, but I can remember 4. I could even use my fingers if I'd like. How many O's are in 2 waters? 2? Yep. Yep. So how many O's in total? 6. So how many O2s do I need? 3. 3. All right? That's the way it works for combustion. I've got one more combustion reaction I want to do, and then there's some homework questions. Yeah, that's right. It's good stuff. Practice, practice, practice. If you can do the homework problems, awesome. If you're struggling a little bit, I've got tomorrow set to practice balancing. I've got another sheet I can find you. There's all kinds of balancing practice we can do. We're going to practice balancing tomorrow all day so that we've got it mastered. Now, you're going to run into trouble on this one, but that's okay. I've done this on purpose to run you into trouble so I can tell you how to fix it. Go with what I've told you. So, I look at the C's first, and right away, what am I putting there? 2. 2. What am I putting there? 3. There's 6 of them. I get half the waters. 3. How many O's have I got on this side? I'm looking on the right-hand side. Just in total, how many O's have I got? How many have I got here? 4. How many I got there? So how many in total? 7. And 7 makes students panic and run away. They scream, they grab their head, and they run away. Ah! Why does 7 make students panic and run away? Yep. It's an odd number. Let's not worry about it. In the actual balancing rules, you cannot have decimals. But we can put a decimal and then we can fix it. If you were allowed to use halves, how many O2s would get you 7 atoms? If you could use halves, how many O2s would get you 7 atoms? What do you got? 3.5. 3.5. Now, yeah, write that down. But it is against the rules, so now you got to fix it. Easy fix. If you want to get rid of a half, double everything.
So I double 3, double 4, double.
I double this 1 to be a 2. I double the 3.5 to become a 7. I double the 2 to become a 4. I double the 3 to become a 6. And it will be balanced. All right? Okay? So that double trick works really well. And it's not just in combustion reactions you can use the double trick. Let's say you're doing something else and you've got an H2. And somehow you got to deal with 3 H2s. Sorry, with 3 H's. You could put 1.5, but then double all the coefficients. And you've then fixed it. Okay? All right. Give them a try, but tomorrow we will be practicing lots of balancing, okay? And I'm going to stop recording.